Let x and b standardized random variables. In other words, their marginals have a mean of 0 and variance of 1. And the correlation between them is rho in the span between -1 and 1, which is totally logical here. We're asked to find the parameters a, b, c, d in terms of rho, such that z and w are uncorrelated, and z and w are functions of x and y. Okay, this sounds like an interesting problem. Let's write down what we know about the random variables x and y. Well, we know that the expectation of x must be 0 because it's standardized. Its variance has to be 1, again by the same argument, and the same holds for y. So the expectation of y is equal to 0 and the variance of y is equal to 1. Now we are also asked that the variance of z has to be equal to 1 by stipulation. Basically, that's what we are assumed to find, and the variance of w has to also be 1, and the same goes for their expectations. Well, basically they have to be 0. Okay, so that is what we know. So let's start by writing down the well, let's do another thing, which is that we know that the correlation of x and y is rho. Okay, and that we know goes varies between -1 and 1. Okay, so let's do also the following, which is that z, I'm just basically writing down what we are given, b of y, and w has to be cx plus dy. So we have 4 unknowns here, a, b, c, d, but we have only two equations to figure out what these 4 parameters are. So we have to set one of them or 2 of them, to set them freely, and then let the others vary whatever we will find given those constraints. Okay, so that's number 1. So let's set such the parameters c and d such that w equals x. And so for that, by assumption, or by selection if you like, because we're basically setting it so that we're saying c is equal to 1 and d equals to 0. Okay, and the next step is now to find the variance of z. So we have now sort of operated on w. Now let's operate on z and then put all things together. So the variance of z, we know is, we just write out what we know z is. It's a x plus b y, and then from here on we just use the definition of the variance, and that is now ax plus by squared expectation minus over ax plus by expectation, and then squaring that. And here, because the square root is just outside of the expectation, we can use linearity, and by linearity we know that this will become expectation of ax plus expectation of by squared, and we can pull out the constants, and we also know that and we know the expectation of x and y are 0 from what was given here. So this whole thing just becomes 0. Okay, that facilitates a bit. And the rest of this term we can just multiply out and see what we end up with. So we have the expectation, and we have a squared like so, plus 2ab xy plus b squared y squared, like that. Now we can use linearity of expectation again, and we end up with the following, and we pull out the constants. You can do that immediately. X squared plus 2ab expectation of x and y plus b squared expectation of y squared. Okay, now these two terms we can figure out by, here on the side we can write, we know that the variance of x has to be, well, that's by definition ex squared minus, like so. We know that the variance has to be equal to 1, and then we know that this term here by standardization is 0. So then this term is just equal to 1. So here this is equal to 1. By the same argument, this is equal to 1. And now what is the interaction between x and y? Well, that, let's see if we can link it to the covariance, because that seems to be the most logical case to start. So the correlation between x and y is then the covariance of x and y divided by the variance of x, variance of y, and all that squared. Now we know that this is equal to 1 and this is equal to 1. So we end up with just the covariance, and the covariance of x and y is just the expectation xy minus the expectation of x y. It became a little short on space. Let's see if we can move this just to make it a little prettier. All right. Expectation of y. Okay. This is an x. And here, okay? So what do we have now? Well, we know that the expectation of x, that's 1, that's 0. And that's 0, so we end up, and then we know that the correlation is the same thing as this term rho that we wrote. So the expectation of xy is just rho. Okay, so now we have our rho entering the game, plus 2ab rho plus b squared. Okay, so now we have calculated the variance, And let's figure out what the correlation between Z and W is. So this is the second equation. Will yield the second equation in our systems equation. All right, so the correlation between the two terms, let's see, what we have here is that we're also given information that they should be uncorrelated. We should find these terms such that they are uncorrelated. So we know that the correlation between Z and W should be 0. All right, so then let's do the following. We write 0 on the other side here. This should be 0, and expand this correlation term and see what we get then. So the correlation is the covariance of Z and W divided by the variance of Z, variance of W, and all that taking the square root over. And now we know that this variance by assumption should be 1 because it's standardized. The same for W. And so we end up with expectation of Z, W, let's just do the covariance now, minus expectation of Z, expectation of W.